Pangaea was a supercontinent that existed during the late Paleozoic and early Mesozoic eras, forming approximately 300 million years ago. It began to break apart around 100 million years after it formed. The single global ocean which surrounded Pangaea is accordingly named Panthalassa. Origin of the concept: the name Pangaea is derived from ancient Greek pan meaning entire, and gaia meaning earth. The name was coined during a 1927 symposium discussing Alfred Wegener's theory of continental drift. In his book The Origin of Continents and Oceans, first published in 1915, he postulated that prior to breaking up and drifting to their present locations, all the continents had at one time formed a single supercontinent which he called the continent. The name occurs in the 1920 and 1922 editions of Die Entstehung der Kontinent und Ozean, but only once, when Wegener refers to the ancient supercontinent as the Pangaea of the Carboniferous. Formation of Pangaea. The forming of supercontinents and their breaking up appears to have been cyclical through Earth's history. There may have been many others before Pangaea. The fourth last supercontinent, called Columbia or Nuna, appears to have assembled in the period 2.0 1.8 Ga. Columbia Nuna broke up and the next supercontinent, Rodinia, formed from the accretion and assembly of its fragments. Rodinia lasted from about 1.1 billion years ago until about 750 million years ago, but its exact configuration and geodynamic history are not nearly as well understood as those of the later supercontinents, Pannotia and Pangaea. When Rodinia broke up, it split into three pieces: the supercontinent of Proto-Laurasia, the supercontinent of Proto-Gondwana, and the smaller Congo Craton. Proto-Laurasia and Proto-Gondwana were separated by the Proto-Tethys Ocean. Next, Proto-Laurasia itself split apart to form the continents of Laurentia, Siberia and Baltica. Baltica moved to the east of Laurentia, and Siberia moved northeast of Laurentia. The splitting also created two new oceans, the Iapetus Ocean and Paleozoic Ocean. Most of the above masses coalesced again to form the relatively short-lived supercontinent of Pannotia. This supercontinent included large amounts of land near the poles and, near the equator, only a relatively small strip connecting the polar masses. Pannotia lasted until 540 AMR, near the beginning of the Cambrian period, and then broke up, giving rise to the continents of Laurentia, Baltica, and the southern supercontinent of Gondwana. In the Cambrian period, the continent of Laurentia, which would later become North America, sat on the equator, with three bordering oceans: the Panthallassic Ocean to the north and west, the Iapetus Ocean to the south and the Conti Ocean to the east. In the earliest Ordovician, around 480 AMR, the microcontinent of Avalonia, a landmass incorporating fragments of what would become eastern Newfoundland, the southern British Isles, and parts of Belgium, northern France, Nova Scotia, New England, Iberia and northwest Africa, broke free from Gondwana and began its journey to Laurentia. Baltica, Laurentia, and Avalonia all came together by the end of the Ordovician to form a minor supercontinent called America or Laurasia, closing the Iapetus Ocean. The collision also resulted in the formation of the Northern Appalachians. Siberia sat near America, with a Conti Ocean between the two continents. While all this was happening, Gondwana drifted slowly towards the South Pole. This was the first step of the formation of Pangaea. The second step in the formation of Pangaea was the collision of Gondwana with America. By Silurian time, 440 AMR, Baltica had already collided with Laurentia, forming America. Avalonia had not yet collided with Laurentia, but as Avalonia inched towards Laurentia, the seaway between them, a remnant of the Iapetus Ocean, was slowly shrinking. Meanwhile, southern Europe broke off from Gondwana and began to move towards America across the newly formed Rheic Ocean. It collided with southern Baltica in the Devonian, though this microcontinent was an underwater plate. The Iapetus Ocean's sister ocean, the Conti Ocean, shrank as an island arc from Siberia collided with eastern Baltica. Behind this island arc was a new ocean, the Ural Ocean. By late Silurian time, North and South China split from Gondwana and started to head northward, shrinking the Proto-Tethys Ocean in their path and opening the new Paleo-Tethys Ocean to their south. In the Devonian period, Gondwana itself headed towards America, causing the Ural Ocean to shrink. In the early Carboniferous, northwest Africa had touched the southeastern coast of America, creating the southern portion of the Appalachian Mountains, and the Meseta Mountains. South America moved northward to southern America, while the eastern portion of Gondwana headed toward the South Pole from the equator. North and South China were on independent continents. The Kazakhstania microcontinent had collided with Siberia. Western Kazakhstania collided with Baltica in the late Carboniferous, closing the Ural Ocean between them and the western Proto-Tethys in them, causing the formation of not only the Ural Mountains but also the supercontinent of Laurasia. This was the last step of the formation of Pangaea. Meanwhile, South America had collided with southern Laurentia, closing the Ural Ocean and forming the southernmost part of the Appalachians and Ouachita Mountains. By this time, Gondwana was positioned near the South Pole and glaciers were forming in Antarctica, India, Australia, Southern Africa and South America. The North China block collided with Siberia by late Carboniferous time, completely closing the Proto-Tethys Ocean. By early Permian time, the Cimmerian plate split from Gondwana and headed towards Laurasia, thus closing the Paleo-Tethys Ocean, but forming a new ocean, the Tethys Ocean, in its southern end. Most of the land masses were all in one. By the Triassic period, Pangaea rotated a little and the Cimmerian plate was still traveling across the shrinking Paleo-Tethys, until the Middle Jurassic time. The Paleo-Tethys had closed from west to east, creating the Cimmerian orogeny. Pangaea, which looked like a sea, with the new Tethys Ocean inside the sea, had rifted by the Middle Jurassic, and its deformation is explained below. Evidence of existence. Fossil evidence for Pangaea includes the presence of similar and identical species on continents that are now great distances apart. For example, fossils of the theropsid Lystrosaurus have been found in South Africa, India and Australia, alongside members of the Glossopteris flora, whose distribution would have ranged from the polar circle to the equator if the continents had been in their present position. Similarly, the freshwater reptile Mesosaurus has been found in only localized regions of the coasts of Brazil and West Africa. Additional evidence for Pangaea is found in the geology of adjacent continents, including matching geological trends between the eastern coast of South America and the western coast of Africa. The polar ice cap of the Carboniferous period covered the southern end of Pangaea. Glacial deposits, specifically till, of the same age and structure are found on many separate continents which would have been together in the continent of Pangaea. Paleomagnetic study of apparent polar wandering paths also support the theory of a supercontinent. Geologists can determine the movement of continental plates by examining the orientation of magnetic minerals in rocks. When rocks are formed, they take on the magnetic properties of the Earth and indicate in which direction the poles lie relative to the rock. Since the magnetic poles drift about the rotational pole with a period of only a few thousand years, measurements from numerous lavas spanning several thousand years are averaged to give an apparent mean polar position. Samples of sedimentary rock and intrusive igneous rock have magnetic orientations that are typically an average of these secular variations in the orientation of magnetic north because their magnetic fields were not formed in an instant, as is the case in a cooling lava. Magnetic differences between sample groups whose age varies by millions of years is due to a combination of true polar wander and the drifting of continents. The true polar wander component is identical for all samples, and can be removed, leaving geologists with a portion of this motion that shows continental drift and can be used to help reconstruct earlier continental positions. The continuity of mountain chains provides further evidence for Pangaea. One example of this is the Appalachian Mountains chain which extends from the southeastern United States to the Caldonides of Ireland, Britain, Greenland, and Scandinavia. Rifting and breakup. There were three major phases in the breakup of Pangaea. The first phase began in the early Middle Jurassic, when Pangaea began to rift from the Tethys Ocean in the east to the Pacific in the west, ultimately giving rise to the supercontinents Laurasia and Gondwana. The rifting that took place between North America and Africa produced multiple failed rifts. One rift resulted in a new ocean, the North Atlantic Ocean. The Atlantic Ocean did not open uniformly. Rifting began in the north-central Atlantic. The South Atlantic did not open until the Cretaceous, when Laurasia started to rotate clockwise and move northward, with North America to the north, and Eurasia to the south. The clockwise motion of Laurasia led to the closing of the Tethys Ocean. Meanwhile, on the other side of Africa and along the adjacent margins of East Africa, Antarctica and Madagascar, new rifts were forming that would not only lead to the formation of the southwestern Indian Ocean but also open up in the Cretaceous. The second major phase in the breakup of Pangaea began in the early Cretaceous, when the minor supercontinent of Gondwana separated into multiple continents. About 200 AMA, the continent of Cimmeria, as mentioned above, collided with Eurasia. However, a subduction zone was forming, as soon as Cimmeria collided. This subduction zone was called the Tethyan Trench. This trench might have subducted what is called the Tethyan Mid-Ocean Ridge, a ridge responsible for the Tethys Ocean's expansion. It probably caused Africa, India and Australia to move northward. In the early Cretaceous, Atlantica, today's South America and Africa, finally separated from eastern Gondwana, causing the opening of the South Indian Ocean. In the Middle Cretaceous, Gondwana fragmented to open up the South Atlantic Ocean as South America started to move westward away from Africa. The South Atlantic did not develop uniformly. Rather, it rifted from south to north. Also, at the same time, Madagascar and India began to separate from Antarctica and move northward, opening up the Indian Ocean. Madagascar and India separated from each other 190 AMA in the late Cretaceous. India continued to move northward toward Eurasia at 15 centimeters a year, closing the Tethys Ocean, while Madagascar stopped and became locked to the African plate. New Zealand, New Caledonia and the rest of Zealandia began to separate from Australia, moving eastward towards the Pacific and opening the Coral Sea and Tasman Sea. The third major and final phase of the breakup of Pangaea occurred in the early Cenozoic. Laurasia split when North America Greenland broke free from Eurasia, opening the Norwegian Sea about 60–55 AMA. The Atlantic and Indian Oceans continued to expand, closing the Tethys Ocean. Meanwhile, Australia split from Antarctica and moved rapidly northward, just as India had done more than 40 million years before. It is currently on a collision course with Eastern Asia. Both Australia and India are currently moving northeast at 5–6 centimeters a year. Antarctica has been near or at the South Pole since the formation of Pangaea about 280 AMA. India started to collide with Asia beginning about 35 AMA, forming the Himalayan orogeny, and also finally closing the Tethys Seaway. This collision continues today. The African plate started to change directions, from west to northwest toward Europe, and South America began to move in a northward direction, separating it from Antarctica and allowing complete oceanic circulation around Antarctica for the first time. This motion, together with decreasing atmospheric carbon dioxide concentrations, caused a rapid cooling of Antarctica and allowed glaciers to form. This glaciation eventually coalesced into the kilometers-thick ice sheets seen today. Other major events took place during the Cenozoic, including the opening of the Gulf of California, the uplift of the Alps, and the opening of the Sea of Japan. The breakup of Pangaea continues today in the Red Sea Rift and East African Rift. See also, List of supercontinents, History of Earth, Supercontinent Cycle, Pangaea, a data library for Earth system science, operated by the Alfred Wegener Institute for Polar and Marine Research. References. External links, USGS Overview, Map of Triassic Pangaea at Paleomaps, NHM Gallery.